Finally, the last piece of the world of insulators, which I would like to cover today, is vocabulary around pollution. First of all, what is pollution? Pollution is anything that flies around a line where you can have dust airborne that will generate a little bit of conductivity on the surface of the insulators. And I show you here a small video which was made in Chile by our colleagues from Brazil. You see you have electric activity on the surface of the insulator, and this is the result of surface conductivity resulting from deposits on the surface of the insulator. So what happens when you have pollution? Well, you have electric activity like you saw before, but if this electric activity is strong enough, it will generate a flashover. So the process is simple. You have airborne dust that will come and sit on the insulators. Once the insulators are dirty, of course, you get always a little bit of fog or a little bit of drizzle, slight rain, which makes that this dust is wet. If it is wet, it becomes conductive. If it is conductive, you start having some electric discharge activity, which can result in a flashover. So pollution is something that is not good for the insulator string, and we have to find solutions to avoid this. Typically, and you probably have seen many insulators like that in China, dust, either dust from the desert or industrial dust, will actually sit on the insulators and work like a sponge when you have some moisture. So there are two words you need to know when we are talking about pollution. They're actually acronyms. The first is ESDD. ESDD is an acronym which means equivalent salt deposit density. So what is this beast? When you have dirt on an insulator, you take water and you wash your insulator. What you're going to measure is the difference of electric conductivity of the water before and after cleaning. And the difference of conductivity represents what we call the ESDD, which is how much conductivity you gain on your insulator because of salts which are contained in this dust. Salts are going to dissolve in water and increase the conductivity of the surface of your insulator. So that's the first number. There is a second number. If I take now my dirty water, I put it through a filter, I dry all that dust in an oven, and I put that on a scale to look how much weight I have of dust on my insulator. This weight of dust divided by the surface over which I have washed my insulator gives me what we call the NSDD, and this is an acronym for non-soluble deposit density. Now this time NSDD will characterize a sponge effect. By this I mean that when you have moisture, humidity, light rain on a dirty insulator, this humidity will actually dissolve the salts, which is my ESDD, and my NSDD will work like a sponge by absorbing moisture so that my insulator becomes wet and conductive. And this is how you generate an electric arc along a string of insulators when you have pollution. So here you have a few more definitions. On an insulator, we define what is called leakage distance. The leakage distance is the distance that the electric current that is leaking in this wet surface is going to have to cover in order to go on the other side of my insulator string. So unlike the arcing distance, which I explained earlier, which is the shortest possible path for an arc, the leakage distance is actually following the shape of my insulator, because if there is a leakage current, which is a current generated by the presence of a wet surface on my insulator, the leakage current is going to follow the surface of my insulator one after the other in order to go on the other side of the string. So in pollution conditions, the main parameter to consider, not the only one, because shape matters, but a very important parameter when you design insulators for a polluted environment is what we call the leakage distance. It is a distance to cover on the surface. And the current that is leaking from the power line through the surface that is polluted is what we call the leakage current. You will see in our catalogs graphs like this. If you remember my ESDD and NSDD definition, you have here graphs where the horizontal axis is ESDD, the vertical is NSDD. Both numbers combined together are going to define if I have a pollution that is mild, medium, severe, and based on experience, we're going to offer one given shape of insulator more than another one, and a certain leakage distance for certain conditions. As you can see here, this is another word that is used when we are talking about pollution. It is what you call USCD. USCD is an acronym which stands for Unified Specified Creepage Distance. So basically, this is the creepage distance phase to ground of an insulator string that is recommended for a certain type of pollution. So if you take, for example, on this graph, section D, which is heavy pollution, which is a result of a certain ESDD and NSDD, you see that the recommendation of the standards is to use an insulator string that is made with 43.3 millimeter per kV face to ground. So that's a recommendation in order to accommodate the leakage current in such a way that it does not become critical. If you have less pollution, you will need less USCD. For example, if you are in light pollution, you're going to need 27.8 millimeter per kV. So depending how long your string of insulators is going to be, you're going to use one or the other shape of insulator with a certain number of insulators in order to match this requirement for the leakage distance. This is how we design insulator strings for polluted conditions. Now, when you don't have any other solution, when you cannot find the right shape and you cannot put enough leakage distance for a certain type of pollution, today, many people are using silicon-coated glass insulators. Why? Because silicon has this characteristic to be hydrophobic. Hydrophobicity is a word that describes the ability of a material to shed water and not be wet. So you see on these pictures, this is a Sediver insulator with silicon coating. You see we have very small water droplets everywhere, but you don't have a big patch of water that is covering the surface of your insulator. So typically in this case, if you have pollution, your leakage current remains low because the surface is not wet. It remains relatively dry. So this is what has been used for many years in extreme pollution conditions. You see here small videos showing you on the right a surface that is not hydrophobic. The water becomes flat on the surface, so the entire surface becomes conductive, versus on the left of this slide, where you see that the water droplet on a hydrophobic surface remains nice and round and will roll off with wind or whatever condition around. So when you use a silicone surface, which can be used either with what we call polymer insulators, which are insulators made of silicone rubber, or a silicone-coated glass insulator where the surface is made of silicone rubber, you benefit of this property called hydrophobicity, so that the insulator remains dry and will have a better pollution performance. Now, my story is right, but in fact, it is not. Of course, a silicone surface will remain dry, but you will not prevent dust from accumulating on the surface of the insulator. So that at the end of the day, I have an insulator that is nice and hydrophobic, but still, on the surface, I will have my dust. My dust is still going to come on it. The beauty of silicone rubber is that this hydrophobic property will actually migrate through the pollution layer in such a way that the pollution layer itself becomes hydrophobic. So if you remember what I explained earlier, ESDD and SDD, the pollution process is a result of a conductive surface, which is wet. If I can prevent the surface from remaining wet, I will also prevent the leakage current from taking place. And in that case, I have a pollution performance that will be much, much better. I just give you here one example. It's a picture from South Africa, Cape Town. This is a place where you have salt spray coming from the ocean directly on insulators. And we have been measuring the leakage current on different types of insulators. So you see here on the horizontal axis, you have 24 hours of time. The vertical axis is the leakage current. The blue and the red curves show you that in the morning, where you have a little bit of fog, you have some dew points, surface of insulators are wet, you have a high leakage current. Then the sun comes out, insulators are drying out, and the leakage current goes down for the entire day until the end of the day where moisture comes back in and the leakage current goes up. If you look at the curves, the black and the green curves, which are much lower and stay relatively stable over time, these are the same insulators, but the surface is coated with silicone. In that particular case, the leakage current is under control, which means that along the coast, these coated insulators are going to have a much better performance than non-coated insulators. And the limit that we have with our glass insulators, whatever the shape, is that at some point in time when you have really high pollution conditions, our insulators are not going to make it. So you have two options. Either you're going to use what we call polymer insulators, like the picture on the left, which are also called composite insulators, which are also called by some people as NCI, which is an acronym for non-ceramic insulators. So when you have extreme pollution, one option is to use polymer insulators. The other option is to use glass insulators with silicone coating, which coating gives the same property under pollution than a polymer insulator. What is interesting in this slide is that these are pictures from polymer insulators and silicone coated insulators, which were in South Africa in that location I showed you earlier. And you see that after a few years, the polymer insulators started to degrade. And those cracks which you see in this polymer insulator is what we call erosion. Erosion is something where your surface is degraded. You have materials that is missing because the electric activity has been eating away. The electric activity has been eating away the rubber. Of course, the same thing happens, as you can see on the right, with silicone-coated insulators. You also have erosion. The reason why we are successful with silicone coating is because underneath the coating, even if you have erosion, nothing is going to happen because you have good old glass. With the polymer insulators, which are at the left of this slide, once you have erosion that goes down through the thickness of the rubber, then moisture is going to damage the core internally and your insulator will break. So the success we have over the last years with silicone coating is that we bring an alternative for extremely high polluted conditions to polymers, which life expectancy is limited by this aging, which we call erosion. This will conclude my presentation.